Here, you observe outliers in features like medical insurance, population, and house price, which adversely affect model performance. It's essential to address them for improved model accuracy. Now let's create a function, remove_outliers, that iterates through each column to calculate the lower and upper bounds based on the interquartile range and replaces outliers with these bounds. This approach preserves dataset integrity by retaining potentially valuable insights from outliers while reducing their impact on statistical analyses and machine learning models. The clean data frame housing_df_new is returned without the outlier values. Let us now visualize the distribution of predictors and the target variable in the clean data frame, housing_df_new, using box plots to observe the impact of outlier removal on the data distribution and potential changes in the feature ranges. This will help in assessing the effectiveness of the outlier removal process. The diagram above depicts the dataset features after replacing outliers with the lower and upper bounds. It ensures extreme values are within reasonable limits. Let us now fit the linear regression model on the clean data frame, housing_df_new. The selected columns are converted to numeric. A constant is added to include the intercept, And then the OLS regression model is refitted to evaluate the model's performance after outlier removal. Now, let's visualize the distribution of residuals and the relationship between residuals and predicted values for the refitted linear regression model on housing_df_new. The histogram displays the residuals distribution, and the scatter plot illustrates residuals against predicted values, while also printing the updated model coefficients to interpret the impact of each feature on the house price. Residuals distribution. The histogram now shows a more bell-shaped distribution that is tighter and more symmetric, indicating that the extreme values, outliers, have been removed, and the residuals are more normally distributed. Residuals versus predicted. The scatter plot displays a more evenly distributed cloud of points around the zero line, indicating consistent residual variance. The range is reduced without outliers. The updated model coefficients indicate the impact of each feature on the house price, with average bedrooms showing the most significant positive influence and average rooms having negative impacts. Let us now compute and interpret the R-square and MSE metrics for the refitted linear regression model on housing_DF_new to evaluate its performance. The R-square score measures the proportion of variance in the dependent variable explained by the independent variables, while MSE quantifies the average squared difference between the predicted and actual values, providing insights into the model's accuracy after outlier removal. Here, we can see that without outliers, the R-square score increased from 0.540 to 0.618, indicating a better fit. MSE decreased from 0.613 to 0.490, showing improved prediction accuracy. Outlier removal notably enhanced the model's predictive capability. This structured process covers all aspects of linear regression, starting with getting the data ready to evaluate the model. It includes checking assumptions and assessing multicollinearity, ensuring a thorough examination. Additionally, the inclusion of outlier removal showcases the importance of data preprocessing techniques in enhancing model accuracy and reliability. By following these steps, you'll gain insights into both the theoretical aspects and practical applications of linear regression, ensuring a solid foundation for further study or application in real-world scenarios. Critical assumptions for linear regression. Regression, as you know, is a parametric approach, where assumptions about data are made for the purpose of analysis. This makes regression restrictive. Successful regression analysis requires validation of the assumptions made. Some important assumptions in regression analysis are the dependent or the response variables, and the independent or the predictor variables have a linear and additive relationship. For a predictor variable x and a response variable y, a linear relationship implies that a change in response y due to one unit change in x remains constant regardless of the value of x. Similarly, an additive relationship implies that the effect of x on the response y is independent of other variables. The error terms are normally distributed. The independent variables are not correlated. That is, multicollinearity between independent variables does not exist. Error or residual terms are not correlated. That is, autocorrelation is absent. The error terms have constant variance. That is, they show homoscedasticity. The presence of non-constant variance is called heteroscedasticity. These were some of the critical assumptions for linear regression. In the next video, we will learn about logistic regression. Logistic regression. Logistic regression is a statistical analysis method used to predict a data value based on prior observations of a data set. Statistically, logistic regression helps to find the relationship between qualitative, discrete dependent variables and several independent variables. It is a machine learning method used in the classification problem to distinguish one class from another. The simplest case is a binary classification. The algorithm is more like answering the given question, and if the answer is positive, it belongs to a set of positive points. If not, it belongs to the negative point class. Many problems require a probability estimate as output. This algorithm is efficient in calculating probability. In logistic regression, the main goal is to accurately predict the class of the two possible labeled data points. A logistic regression model ensures that the output always falls between 0 and 1. As we use a sigmoid function, the image is the formula of a sigmoid function to map probability predicted values. We need to use the sigmoid function. This function maps any real value to the other value between 1 and 0. We use the sigmoid function to map prediction to probabilities. There are two types of logistic regression. They are binary, for example, 0 or 1. Multinomial, for example, 0, 1, or 2. Decision boundary. The probability score we get by using the algorithm is between 0 and 1 based on the inputs we provide. For example, let's consider we have two products with one being eco-friendly and the other being toxic. We have a threshold value to classify the given product. Application prediction of a cricket match outcome, assessment of presence or absence of fraud, financial transactions based on banking activity, assessment of erosion of seabed. Due to fishing activity, prediction of crash based on tidal energy and icebergs. Prediction of bankruptcy using logistic regression. This was all about logistic regression. In the next video, we will learn about oversampling using SMOT. Data exploration using SMOT. In this video, we'll see how to prepare the data, explore and visualize the data, train the logistic model, and also how to evaluate data. Let's start by importing the required libraries. We are using the Cuisine dataset. Let's check the observation. Here we have the cuisine and different ingredients which have been used in the cuisine. Based on the ingredients, we have to predict which cuisine it belongs to. Let's check the info. As you can see, there are 385 columns and 2,448 observations. Let's plot this and see how many cuisines we have. We can plot this in a bar chart. As you can see, Korean is the highest and Thai is the least. These are all finite numbers. Let's create a function called create, ingredients based on each cuisine. Let's see what are all the ingredients that are present. Based on that, let's see if we can remove it or see what are the common ingredients so that we can do some data exploring. Let's start by creating a data frame for each of the cuisine. So for each cuisine, we have created a different data frame. Let's print this using the print function. We have already seen this in the graph, but let's print and see the data shape for the same. As we can see, these are all the datasets we have. Let's create a function called createIngredients, so that for each cuisine, we know how many ingredients have been used. Let's go ahead and create that. We're dropping cuisine column and unnamed 0. Now we have defined the createIngredient function. Let's check the ingredients for Thai first. Let's plot first 10 ingredients. Here, garlic has been used frequently, and then fish and so on. Let's check for Japanese as well. What are the common ingredients used? As you can see, in Japanese cuisine, soy sauce has been used the highest, and then rice, vinegar, vegetable oil, and so on. Similarly, let's check for Chinese. Again, soy sauce, garlic, and ginger have the highest usage. As you can see, in all the cases, ginger, garlic, and rice have been used frequently. Now, let's check for Indian cuisine. In Indian cuisine, cumin, turmeric, onions, ginger, and garlic have been used. Let's also check for Korean. Again, garlic and rice are the frequently used ingredient. Since there are common ingredients used, we can create a feature and drop those so that it doesn't influence our model. Let's check the features. As we can see, these are all the features we have. You can also see here, all the cuisines have different numbers or different observations. Our model can influence and predict it as Korean. We call this as imbalanced dataset. To balance this, we can use a technique called SMOT. Let's implement SMOT and make it a balanced dataset. Here, we're using oversampling from SMOT technique. We have transferred. Now let's print it. Let's compare with the whole table. As you can see, all the cuisine we have now are 799. We can also see the original data we had earlier. Let's fit the logistic regression model. Now, let's import the libraries which are required to plan logistic regression. Let's split our data to test and train. Here, we are using 70/30 ratio. Let's fit the logistic regression. Let's calculate accuracy. Accuracy is 80%. Let's consider one ingredient and try to break the probability. Let's see the probability of each of the ingredients. Let's print it. The ingredients we have here are black pepper, onion, soybean, etc. These are the ingredients we have for Korean. Let's test what our model will predict. If we directly predict, it will give us the number. Since we want probability, we're using predict prob function. Let's sort the values. As you can see, our model is able to predict Korean as high probability, and next is Japanese. We have now got the probability for each of the cuisines. Let's check the classification report. The classification report will give you the overall accuracy, which is 80% as we saw earlier. It will also give us a precision recall for each of the outcomes. As you can see, for Indian cuisine, It has predicted 92%, and next is Korean at 83%. This is how we can see how it performs for different outcomes. In this video, we learned how to prepare the data and cleanse the data. We created an EDA on how differently ingredients are related to cuisine. We learned how to balance the data, since it was an imbalanced dataset. We also learned how to fit the model and evaluate it using the classification report. Oversampling using SMOTE, a dataset that contains observations in one of the classes that are much higher or lower than the other classes, is called an imbalanced dataset. To correct the data bias of one class over another, we perform oversampling by the synthetic minority oversampling technique, or SMOTE. SMOTE is a data augmentation technique that helps balance data distribution by adding to the minority class examples. This is done by generating training records between existing minority instances using linear interpolation. Consider this visual representation of a dataset on your screen. Class 1 here is a minority class with a lower number of observations. If we apply SMOTE to this class, it would join the points with line segments and place artificial points along those lines and balance the data distribution. The SMOTE algorithm works in this: select an input vector from the minority class, find its k nearest neighbors, build a line joining the point under consideration and the chosen neighbor, place a synthetic point anywhere on the line drawn, repeat steps 1 to 4 until data is balanced. Applications. SMOTE is used to balance data for classification problems where one class is more than another. It can be used in the classification of job roles or individuals based on the agility requirements of teams. Teams are usually unbalanced datasets. It helps increase decision boundaries. It helps improve classification performance by enhancing the probability distribution of datasets. Polynomial regression expresses the relationship between a dependent variable and an independent variable in a linear manner. When data is more complex, as shown in the figure, we cannot use linear models to fit nonlinear data. To overcome this drawback of linear regression, we use a modified version of it, called polynomial regression. Polynomial regression is a statistical method used in machine learning for predictive modeling and analysis. It is a form of linear regression that models the nonlinear relationship that exists between a dependent variable, y, and an independent variable, x, as an nth degree polynomial. From this figure, we can observe that the straight line is unable to capture the patterns in the given data. To achieve a higher-order equation that captures complex data patterns, we can add powers of the original features as new features. Hence, the linear model can be transformed to, despite the transformation, it is still considered a linear model due to the linear nature of the coefficients or weights associated with the features. Here, x2 is only a feature, but the curve that we are fitting is quadratic. It doesn't capture some data points, as we can see in this figure. Thus, to capture more data points and convert the original features into their high order, we use the polynomial features class provided by scikit-learn. After applying the polynomial regression, we get this graph. It is clear from this graph that polynomial regression provides us the best approximation of the relation between a dependent and an independent variable by capturing most data points and decreasing the error between the actual data point and the predicted data point. Hence, we can say that the model has been trained properly. Applications of polynomial regression machine learning techniques that use polynomial regression can be used to develop climate model predictions that run faster and more efficiently, predict the rise of different diseases within populations and their spread rate, study the isotopes present in sediments, and examine the generation of any synthesis. In this video, we have discussed polynomial regression. In the next video, we will learn data preparation, implementing the model and testing performance.
Data preparation, model building, and performance evaluation, Part A. In this video, we'll see how to fit the polynomial regression. Let's start by importing the required libraries. To begin with, let's consider a salary dataset. As we see here, we have 3 columns and 10 rows. Now that we have fit the model, let's create a function called visLinear. Note we are fitting a regression line based on salary and position level. Now, what we see here is, even though we fit the line, the data points are still scattered and have not fit with the line. So now, let's fit polynomial regression and see how it performs in this case. For which, we have to import the label from pre-processing. So here we are fitting the polynomial feature at degree 4. Let's choose a degree at 4 and transferring back to our X data to fit into the linear model. Now, let's create a different function for polynomial regression. Polynomial regression is generally used when the data points are not captured by the linear regression model and the linear regression fails in describing the best result clearly. Our agenda here is to fit the data points to the line using polynomial regression. The result of this is as we see here. Majority of our actual data is fitting the line. Now, let's try to predict for one value using predict function. So if we have used the linear regression model, we would have predicted the value as 2,49,500. However, for polynomial model, the prediction is 1,32,000. Clearly, you can see the difference. So that's the reason we use polynomial regression. where your data is nonlinear and not able to fit the line to that data set.
Ridge regression. Ridge regression is a form of regression that shrinks the coefficient towards zero to reduce the complexity of the data. This technique discourages the use of complex models and reduces the risk of overfitting. It decreases the multicollinearity between features in the dataset. It also minimizes the variance of the model without increasing its bias. This regularization technique involves a loss function also known as residual sum of squares, or RSS. RSS is nothing but the difference between the actual and predicted values. Let's take an example where y is equal to beta 0 plus beta 1x1 plus beta 2x2 plus up to beta pxp. Y is the independent variable. Beta is the regression coefficient value, x is the dependent variable. Here, lambda is the constant or the tuning parameter that decides the appropriate rate to penalize the flexibility of the model. When lambda equals 0, the penalty term has no effect, as penalty is a multiple of lambda and the sum of square of weights. When lambda is infinity, the impact of the shrinkage penalty grows and the ridge regression coefficient estimates will approach 0. This will result in a less complex dataset, which in turn helps us get the best fitting model. Applications of ridge regression. We use ridge regression to eliminate multicollinearity in data models. For example, the technique is used in the hospitality industry to manage seasonal fluctuations in the booking prices of hotels or resorts. Ridge regression models are used in farming as an effective method to predict grain yield under different water regimes. Data preparation, model building, and performance evaluation. Part B. Welcome to ridge regression. In this video, we'll see how to implement the ridge regression. This is also called regularization. Let's start by importing the variables. Median is the dependent variable, or the target which we will be predicting. Let's check the info. We have 506 observations and 14 columns. You can see this is the same dataset that we choose for fitting the regression. As you can see, there are no missing values. Let's create independent and dependent variable. Let's split the data. Now, let's fit the model. Let's keep the alpha at 1. Now, what we see here is the intercept value is 24. Let's see what is the mean square error. RNC is 4.74. Let's check the coefficient of the model and also check R2 score. .67 is the R2 score. Now, let's use the grid search. Here we are defining a grid. First, let's create a dict. That's a negative mean absolute error. Now, let's read the result. The score is minus 3.5 and the configuration. Fusion is alpha as plus 0.7. Let's fit this with alpha points and try to predict. We can also check the evolution matrix. Now we see that the RMSE is 4.731. Compared to earlier, it has reduced slightly, as it was 4.741. But let's check the R2 score. R2 score is 0.678. It does not change much, but yes, it's slightly increased. Let's check the coefficient of ridge regression. As you can see a lot of negatives, it has penalized. If you see the earlier ones, not much of a penalization as compared to the optimal alpha value. So this is how you rid the data and fit the ridge regression. Lasso regression. Lasso regression is a form of regression that shrinks the coefficient towards zero. This is